Okay, so welcome to lecture 5. I hope you enjoyed your day Tuesday. So let's start with the summary of last week again. So we had on Tuesday last week, we had this simple example of field theory by looking at phonons. And so we looked at two different approaches. One was the direct solution of the 1D exact system, where we're looking at particles that are connected to each other and they are moving in space. And we described the deformation as un minus 1 and so on. And so what we saw when deriving their dispersion relation was that there's a universal behavior of the dispersion relation as temperature is small. And what we found is that the frequency depends on the on k with a constant v, where only this velocity v holds the interaction specifics. But the general relationship of frequency being linear and k is universal. And so that, for example, also led to one of our main measures, the specific heat. C to be linear in temperature, also universal property. And that all despite this phonons really being a collective behavior, because all the particles are sort of deforming in a long range, long wavelengths way. So despite this collective long range dynamics. And so that gave us a taste that even if we're looking at interacting particles where there's long range dynamics, we may be able to describe them in simple terms and understand how this universal behavior applies. And so the other approach to show that was then to derive a field theory where we now don't have the individual particles anymore, but we're looking at a field of deformation, U of x. And then we here build the potential energy from general principles. And these were locality. And then we used translational and mirror symmetry. And the stability of the system. And so based on that, we could write down a generic potential. And when looking at the potential, we could really easily read off the dispersion relation, which with much less work. So that was easy to get, but what we lost along the way was that V is like, it's a material specific constant, we know that, but it's unknown how it relates to the microscopic properties of the system. And so we lose something, but we have not only that it was much easier to derive the dispersion variation, but we had the big gain, which was that this was now easy to generalize to arbitrary dimensions. And so, for example, we found that the specific heat scales with the temperature to the power of the dimension we're looking at. And so that's the big gain of looking at field theories, because in the exact system, if you would go to like a cubic lattice, it would have been a lot more pain to really go through the calculations in Fourier space. So that was the motivation of field theory, and then we start with the sort of main outline of the class by looking at models. The most notable one that you should really know by, you will know by heart, I have my full trust, is the Ising model, where the Hamiltonian is given by minus j interaction strength, summing over ij si sj, and there's an applied field that acts on the spins of the system as well. And we looked into a plethora of more. One just to point out, because we're going to look into it also a couple of times, is the ON model, where we generalize the Ising model to spins that have not just 2 degrees of freedom, but potentially arbitrary degrees of freedom by looking at them in vector space, describing them as vectors. And then also the applied field becomes a vector, where here we note that the spins are normalized to length 1. And then after having outlined all the models, we looked into exact solutions to the 1D Ising model, so h equals 0, and found that we can derive the partition function exactly to be 2 to the power of n hyperbolic cosine beta j n minus 1. I'm going to keep revisiting that, so it's good to sort of keep it easy to look up as a reference if our calculations were correct. And so, okay, so that's obviously very, that's the easiest case we can solve, like without an applied field. So the next step was to look at exact solutions to the 1D Ising model with applied field. And this is where we found our first new method to solve these kind of problems. Namely, we found that we can write the partition function, which is the sum over products of an exponential, where in the exponential you have the spins, so the exponential can take different forms. We can efficiently write this partition function as the trace of a transfer matrix to the n. Sorry. Where the transfer matrix is, if I'm able to write the Hamiltonian as just product of exponentials, where in the exponential I only have 2 subsequent indices for my spins, so si plus 1, then I can enumerate the different states si1, si minus 1, and si plus 1 equal 1, si plus 1 or minus 1, and evaluate the exponential in all these cases. For the Ising model is given by this. And then we can see that the partition function actually simplifies to just the eigenvalues of this transfer matrix, well, in this case, we have it's a 2x2 matrix, so it's eigenvalues. So we only have 2 eigenvalues of t, sorry, oops. And so then we can see that by writing it as the sum of the power of n of all the sum of the eigenvalues each to the power of n, and rewriting it in this fashion, we see that if lambda minus is the smaller eigenvalue and lambda plus is the bigger eigenvalue, then in the limit of taking n to infinity, because this is a number that's smaller than 1, this actually goes to 0. And so in this case, the partition function is given by just the largest eigenvalue of your transfer matrix, which is true in general, not just for the 2x2 transfer matrix of the Ising model, which we're going to see today or later next week. And so in this case, we found the free energy per spin in taking the limits n to infinity, so only taking care of the largest eigenvalue here. And so we reassured ourselves that this is the correct result by taking the limit of sending h to 0 to then recover the free energy that would follow from this partition function. So for today, we're going to use what we learned here to now calculate for the 1D Ising model with an applied field, the magnetization and the correlation functions. Remember, those were the entities where we could see if there's a phase transition. Do you still remember how we should, what would the magnetization tell us about how could we spot the phase transition in the magnetization? Yeah. I made a pact, actually. I want to learn your names. If you're okay, tell me your name. Then David, okay.
I mean, it's kind of an order parameter. Yeah. So it would be 0 on one side of the phase transition and 1, 0 on the other.
Mm-hmm. And so what's the general property of that this
discontinuity?
Yes, exactly. So you'll have a discontinuity in the magnetization is the first order derivative of the free energy, right? And so you have a discontinuity in the first order derivative. So that's why we care about that. And the correlation function gives us a very different kind of insight. This tells us about like if the fluctuations in the system are long range or not, long range correlated. And looking into this, we will learn about the concept of lower critical dimensions. Right. So off we go. Oops. Magnetization. And so here we're following Yeomans chapter 5. So, so like different books have different orderings of how they introduce the different topics, which apparently, it's I chose to do all the exact solutions and then go into mean field theory. Yeomans chose it the other way around. So that's why we're jumping to chapter 5. So the way we're going to solve, so what we want to solve is we want to get the magnetization, which is the average spin, or it will be this, and and we're interested in, we want to derive the correlation functions, we need the correlations between, say, a spin at 0 and a spin at a distant r. And now the trick is that we remind ourselves of this wonderful tool that we learned last week, which is the transfer matrix approach. So what we do first is we express these two expressions as a function of transfer matrices. So remember, the average spin is given by normalizing with a partition function and then summing over all states, SI and the Boltzmann factor. So this term here looks very similar to what we had solved last week, except for, you know, this spin being on top. So this is similar to before up to SI. And so let me just drag this normalization around. So the way we're going to write it is we're going to try to again write Boltzmann factor as a product of exponentials. Well, we know that the summation over states means that I sum over S1 being plus minus 1 and, you know, up to Sn being plus minus 1. And now the transfer matrix allows me to write this the different exponentials as T1, like the transfer from going from spin 1 to spin 2, and so on, up to I minus 1 Ti. I have Si here in between. Then I go from Ti to I plus 1, and all the way to Tn. And we're still keeping these periodic boundary conditions. So there's n, and n goes to 1. Huh? 1. And so as in a similar fashion as before, I can now I can execute all the sums except for the sum over I, because the for the sum over I have this extra contribution with the SI, but all the others I can in principle execute just as we did last week. So that then reads, I'm left with this SI going from plus 1 minus 1. And so executing means that I end up with I to the power of 1 products which take me from 1 to I, SI, and then I go from I to back to 1, power n minus I plus 1. And so similarly, I can do the same for the correlation. So S0, SR, it's a little more complicated because we have now 2 spins that we have to insert. And so we have to pay a little more attention on which matrix products we execute. So. Oh, sorry. I should I try to be a little more consistent with my notations. I'm sorry. Because I actually start here with 1, so this should be 1, and it should go to R plus 1. So I want to have exactly R is the distance between the two spins I'm considering. So SR plus 1, sorry, plus minus 1, so SN plus minus 1. And then I have this S1, T, and then up to R plus 1, SR, TR plus 1, TR plus 2, and N and 1. And if I then lump this together as before, we are left now with two open summations, 1 over S1 plus minus 1 and 1 over SR plus 1, where we now have S1, and here we have go from 1 to R. These are R steps, R plus 1, sorry. And then we have SR plus 1, and we go from TR plus 1 to 1, and that's another N minus R. I think there's a minus 1. It will cancel out anyway, so it doesn't matter. I go from R plus 1, so I take N minus R plus 1, yeah. And so now we're left to figure out what the heck is this, right? What is this product of my transfer matrix, which we basically have written down here, right? Times the spin and times the another transfer matrix. And so the way we're going to execute this is to remind ourselves that the transfer matrix is a matrix, so the best way to evaluate it is to go into the eigenspace of the system. So evaluate these sums, which oh gosh, oops. Here we go. So that means let me define the eigenstates. So and I'm going to use the quantum mechanical bracket notation. So that's the one eigenvector, which gives me this eigenvalue on the plus, and then I have similarly the other eigenvector, which gives me the smaller eigenvalue. And then what this allows me, if I go to the eigenbasis, then I can express T as the sum over all the eigenvalues, right? So I can write T as the sum over J now being plus or minus for the two different eigenvalues. And lambda J. So the two of the terms. And so similarly, I can then write, say, this Ti1 to the power of I minus 1. I can write it as so now I'm evaluating this matrix as at S1. here I have my different eigenstates, lambda j, and because I have this I minus I times psi j, and then s I. And so using this notation, I can now rewrite the magnetization as 1 over z. This one. So now I'm just copying down. This is rewriting this one. And now rewriting the second product. Where is it? Yeah, second matrix to the power of, also in this the eigenbasis. Sorry, I need another letter because these are two different vectors. So I need a k here too. K, psi k, lambda k to the power of I. No, sorry, n minus I. And psi k S1 again.
It's like lambda k to the power of I or I minus 1.
I've been wondering that too. Let me think about it. It should be I minus 1. Sorry. And sorry, and this was yeah, minus 1. Yeah, that's how it works out. And so now I have what I can do simply is I can move this up down here, move forward, because then I have a product I can evaluate, because here we use that also S1 and Si can be expressed in terms of their eigenvalues. Si and their eigenvectors S1 or Si in a similar fashion as we did for the transfer matrix, right? So we wrote this now as to insert it there. But as this now exemplifies the eigenvalue. And now I move this term forward, so I end up at, sorry, because if I move it forward, what I get is I have this this vector acting on that one, which is equivalent to just having by sum over the states psi k acting on psi j, right? Sorry, let me just make this brackets psi k, which is easy because these are the two eigenvectors of our transfer matrix, and we know they're orthogonal to each other. So this or orthonormal even. This is dkj. Principle, we still have the sum, but it's simplified now considerably because let me just copy down the other terms. Because of this delta functional, popping up. Okay, and so now since we have delta kj, this becomes only a sum over j equal plus minus. And then we have lambda k, and that's why like now these terms drop out, and it's just lambda k to the power of n, lambda j, sorry. And we're left with psi j si psi j. And so similarly, we can arrive at the corresponding result for the common relation. So the idea is, in this derivation, we so far haven't used the explicit form of the transfer matrix for the Ising model. So these equations are general for any transfer model, describable model for now. And similarly for the correlation, again, we get S1, SR plus 1, Z, and now so do I have it? Sorry, I'm scrolling back up. Where's the here? So what we have for the oh, sorry, my notation, I know that's an R. It's an R. Okay. And it's an R. R is a bad choice, I realize. Sorry for that. Okay, so we do the same thing, right? That we here express the transfer matrices in terms of their eigenbases, which then results in these terms. And then similarly, I move the term psi j, and now I have two sums again. So then I move the sum forward like we did here, but now we have two of these terms left over. That's why we have these two sums over jk left, with these two products evaluating spin 1 in the eigenbasis and evaluating the spin at r plus 1. Sorry for that. The other also at the eigenbasis. And now we can even simplify these expressions a tad more, because remember, we actually have derived the partition function, right? And so we know that the partition function is the sum over n equal plus minus lambda n to the power of n. It's just the sum of the eigenvalues to the power of n. And so what we can now do, similarly in finding a simple expression in the limit of large n for the partition function, we can also here divide by the largest eigenvalue, lambda plus to the power of n. And so what we get, and now let me keep going with the correlation function, is then, oh, sorry, this goes away. And then I have lambda j over lambda plus to the power of r. So I'm splitting up what I'm dividing by. and lambda k over lambda plus to the power of n minus r divided by j plus minus, that's the partition function now. And here we have lambda n. Oh, sorry, that's not lambda n over lambda plus to the power. And so now the same game unfolds, that if I now take the limit n to infinity, the terms with the smaller eigenvalues, they don't contribute or they diminish, and so only evaluating using the term in the sum of lambda equal lambda plus, so the largest eigenvalue actually contributes. Note for n to infinity. And lambda plus over lambda plus to the power of n is equal 1, right? So that simplifies now our expression, because the partition function just becomes 1, like not the partition function, it's the normal, like the partition function normalized by lambda plus to the power of n, this becomes 1. And in the above terms, I'm still summing over lambda. Sorry, yeah. I still have the sum j plus minus. So because this only applies if I'm taking to the power of n, right? And so only this term has the eigenvalues to the power of n. So let me just use color. For k and n, so that's regarding this term and this term, right? So only in these two terms, I know that if I'm taking the limit n to infinity, this becomes 1 and this becomes 1. But I still have this term left. Let me just reorder and move this term to the front. And change colors. So then I still have lambda j to the power of lambda plus r, and these matrices that I have to evaluate still. Sorry. And k only contributes at k equal plus. So this becomes lambda plus. And here we have psi j as r plus 1, psi plus. But we can actually spell out the sum in this case, right? Because we know that we're only summing now over two different states, lambda j equal lambda minus and lambda j equal lambda plus. So let's have a look at this. So what this means is that I have psi plus and then we have 1, right? Lambda plus divided by lambda plus is 1. Let me just make my brackets a little more brackety. There we go. And then for the lambda minus case, we have lambda minus divided by lambda plus to the power of r, and then psi plus 1, psi minus is plus 1. So this is the more complicated case, and that's in this step the correlation. So that's why now I'm adding only here the case for the magnetization, because in the magnetization, we only have, go back to the magnetization. Here, we only have one term for the eigenvalues to the power of n, right? So it's much easier because here, if I take the limit n to infinity, only lambda plus contributes. There's no other term that I have to take care of. And so this becomes easier. And so Si is then simply lambda plus Si lambda eigenvalue, eigenvector plus for n to infinity. Okay, so we only looked at the correlation because we're actually interested in the correlation functions, which is measuring the fluctuations, right? So remember the definition of the correlation function. So that was this gamma 1 r plus 1, and that's defined as S1 SR plus 1 minus S the mean values of S1 and SR plus 1. And so now we can, on the basis of this formula, we can already evaluate, because what we have here is that the first term of our correlation function, this is S1, right? And the second term is the mean value of SR plus 1. So these two cancel, and actually our correlation function from 1 to R plus 1 is then simply the second term, lambda minus the lambda plus to the power of R, and okay. And let me also now add the definition of the correlation lengths. And then we're gonna eventually evaluate these matrices in the case of the 1D Ising model. But for now, as I said, like these are general equations. So the definition of the correlation lengths. Sorry. Is taking the limit r to infinity minus 1 over r of the ln of S1 SR plus 1. So this is assuming that there's an exponential decay of the correlation function to the power of minus r, and I want to measure over which length scale this, what dominates this exponential case. So it's e to the power of minus r over xi. This is what I'm assuming. And so this is just expressing this exponential decay as a function, solving it for the correlation length xi, or in this case, xi to the power of minus 1. And so now in our case, with this transfer matrix approach, this simply becomes then to infinity of r ln of now lambda minus over lambda plus. And so you can already see that these two terms cancel, right? And so what is the dominating contribution is actually that this psi is just a minus ln of the ratio of the largest and the large and the smaller eigenvalue. And so just to make this clear, this is generally true for any transfer matrix. This result, this is generally where lambda minus denotes the smallest and lambda plus the largest eigenvalue. So now you may appreciate why we should care about the correlation lengths, because we can have a statement about the correlation length just by knowing the eigenvalues of our transfer matrices, whereas for the magnetization, where we're hunting for this jump in the magnetization, we really have to find our eigenvectors and actually go through the matrix multiplication, which we're actually now going to do in the case of the 1D Ising model. Yes.
Could you say something to the concept of the correlation length? So what's the exact meaning? And
so the idea is
as something to the power of -1.
So the idea is that, sorry, I want to have a proportional. The correlation lengths, the correlation decay with e to the power of r over a certain length scale. And I'm interested in on which length scale does the system decay. So what's the intrinsic property that tells me about the system?
I see. Okay.
And when we're now going to actually really evaluate these functions, then you have examples of how this changes with, say, the temperature of the Ising model, and we can then see if we if we see the behaviors of a phase transition 1 page away, where we have correlations breaking down at high temperatures, right? Obviously, because you have all the fluctuations that are like happily fluctuating, so there's no correlation. But we expect that if at a phase transition, you have long range correlation. So at a phase transition, we wouldn't have an exponential decay, but we would have the power law decay. And then the exponent of this power law decay would be our critical exponent and would be a universal property of this kind of phase transition of the models and materials and whatsoever belonging to this universality class. But as long as we're not at a phase transition, we'd expect such a behavior. And so if we have a power law behavior, then our psi becomes like we have typically a divergence at the phase transition, and so of the correlations, and so this psi becomes divergence means that the xi typically becomes infinite. And so that's why we want to evaluate and look at, is there something happening? Because now we're evaluating it in the model as a function of all temperatures. And so if we then can go to the high temperature limit and the low temperature limit, we know what's happening on the sides. And then we can sort of say something, okay, do we expect the phase transition to happen in between? And then we can try to say something also about the phase transition in between, which in this case, boring, it won't be. So, I mean, I should have said this, right? It's kind of like, oh, look, you're learning all this math here. Just to break the news, the 1D Ising model is very boring, phase transition wise, but anyway, you learn the methods here, but still, it's very useful to look at, to know these methods, and because we can solve this and understand the dynamics of the one-dimensional Ising model, we learn about the concept of the lower critical dimension. So there's certain dimensions where which says that there is a minimal dimension of your system that you need to actually have a phase transition. And it turns out that 1D for the Ising model is below this lower critical dimension that you need to have a phase transition. So that's why if we now actually evaluate these, it's going to be very boring because there is no real phase transition taking place here. But we'll understand why in a really intuitive fashion of why we actually wouldn't expect anything to happen there and why we would expect a phase transition to happen at higher dimensions. So this is providing you with the tool set. Sorry, I have to flip back. Yeah. Okay, and I tried to do the name thing. So that was David. What's your name? So I'm just
Manuel.
but not the German pronunciation, but
I just pronounce it when I talk in English this way.
Okay, that's okay. Yeah, I can cope with that. Yeah. Yeah, I have the same thing that I mean, I happen to have an English name, so I use the English pronunciation when speaking English. I think. Okay, so now let's put in numbers. So remember for the 1D Ising model, we had these eigenvalues that we derived. That was lambda plus minus is e to the power beta of j cos h beta h minus okay, and we got them from the transfer matrix T, where T is given by this e to the beta j plus h minus beta j minus h. And so this transfer matrix also has eigenvectors. I'm kind of trying to spare you from writing down the full eigenvectors, or maybe me. So T has eigenvectors, obviously. And I'm going to denote them as alpha plus, alpha minus, and the other one, which is alpha minus minus alpha plus. So I just take these two variables. That's a shorthand way of make this a nicer alpha of denoting these eigenvectors. Because now I can write down alpha plus minus squared is, and now you can kind of see why I didn't want to go through the exercise of actually writing down the full eigenvectors. Okay. But so okay, so we have the eigenvectors. I remember for the spin, we want to have maybe I should bracket that too. Right, we want the eigenvector associated with the largest eigenvalue acting on the spin states, and so the spin states, and then bracket again with the transpose of this eigenvector. And so the spins are just represented with something that you actually know, the Pauli matrix, right? It's either -1 or -1. And so the spin states are represented by the Pauli matrix. Si is then 1, 0, 0, -1. And so now you can we can get at the magnetization. So that's then S lambda plus, and I'm here dropping the index E because all the spins are the same. And so that's then evaluating alpha plus alpha minus, acting on 1, 0, 0, -1, alpha plus alpha minus. And if you do this, you arrive at sin H beta H divided by okay. Does that make sense? Well, let's check. So we check first at what happens at j = 0. That's easy to evaluate because there we take j equal to 0, that becomes a 1, and I can write a 1 as the 1 is cos hyperbolic cosine squared beta h plus sine plus minus sine hyperbolic sine squared beta h, right? So, and then I have this 1 here. I replace it by cos square minus sine square. The signs cancel, and I can take the square root of the hyperbolic cosine square, so I get sine over cosine. And so then we see that in this limit, S is just tan beta H, which makes sense for, that's the result for a paramagnet. And so if you have a paramagnet, we'd expect that if you send the field to 0, there's no magnetization, right? Because there's no interaction with the spin. So independent of the temperature, there's no applied field, there won't be any magnetization. And so obviously, and 0 interaction, there's no phase transition because we don't ever have for any temperature, any magnetization. So, and so also no jump in the magnetization. So note for H = 0, S 0. And actually this the statement is true also. So this statement is true independent of looking at paramagnet, right? Even if we turn on the interaction, then the magnetization, if I send H to 0, the sign of H equals 0 is 0. So at 0 applied field also for a ferromagnet, we don't have any magnetization. The only exception is if I were to first take the temperature to 0 and then take the field to 0. So if I have an applied field and I'm already at 0 temperature and then I turn off the field, that's the only case where if I take this order of the limits, where I can have a finite magnetization, because the system was fully magnetized at temperature 0 with the applied field. And if I then turn it off, the spins can't flip anymore because there's no temperature to actually flip them. And so then they stay magnetized. So, but this is the only state where, you know, I can have any change in state. So we write H goes to 0 from plus or minus. But we first take the limit of taking the temperature to 0 of this magnetization. Then we can have either a positive or a negative magnetization, depending on which direction we apply the field. Okay, so that was the result for the magnetization. Let's look at the correlation. Remember, this was lambda minus over lambda plus to the power of r. And then again, evaluating now these, that was a minus. And if we put in the eigenvectors as defined, we arrive at e to the okay. And so again, let's look at simple cases. So what happens at 0 field? So taking H to 0, then we'd get a contribution from the ratios of the, so this contribution cancels, right? Because the sign of 0, hyperbolic sign of 0 is 0. These two become 1, and I get a contribution from the ratio of the two eigenvalues, and that's then tan against H power R to J. And so let me just plot this, what this means. So at 0 applied field, our correlation function, we can plot at different temperatures as a function of R. So relation is 1 at R equals 0. And say this is 1, 10, 20. Then I would have this exponential decay for 1 over beta j for 1, say. If I decrease the temperature, this becomes shallower. And only at t equals 0, I have a straight line. So there's a decay for t non-zero, and only at t equals 0, I can have an infinite correlation. And similarly, we can then calculate the correlation length. Remember, we had derived that this is minus ln of lambda minus over lambda plus. And so that's minus ln of, again, longer expression. The minus in front divided by the same, the plus. And again, here we can look at the different limits. So what's the correlation length if we take beta to infinity, which means we take temperature to 0. So what happens is, without like really going in at length into deriving all the steps, what happens is that if we take the temperature to 0, then these exponentials become 1s. And again, I use that I can write 1 as cos h squared beta h minus sine h squared beta h. And so if I insert this here, then the sines squared h, these cancel, and I can take the square root, and then I have these two different dominating terms, and arrive at a scaling that goes with 2 beta h, which means that this goes to 0 if I have 0 applied field, or it goes to actually infinity if I have h unequal 0, because I'm taking beta to infinity, right? So here we have this, recovered this phase transition at t equals 0. So the correlation length, if we take the temperature to 0, but before it's exactly the same case as here, right? So if you take the temperature to 0 first, and only later on set the field to 0, then we can have this jump in the magnetization, which goes hand in hand with an infinite correlation. And if you take the opposite limit, so we take beta to 0, which means that we take the temperature to infinity. Again, sorry, my expectation is oh, sorry. Yeah, sorry. Here my explanation was rubbish. I'm sorry. So if to get to this result, these two terms, sorry, let me do color coding. So if I take beta to infinity, this term becomes 0, right? These two terms become 0. And then I actually have here a cos h beta h minus sine h beta h, which is nothing else but e to the minus beta h. And this is from the top. And then from the bottom, I get cos h beta h plus sine h beta h, and that's e to the plus beta h. Yes, and then you get that the lambda minus over lambda plus becomes e to the power of 2 minus 2 beta h, and then taking the ln, you arrive at this result. And I already give you the derivation for sending beta to 0, because then these terms become 1, and then I use this relationship to arrive at having the ln of something negative, right? Something 0. So because then I have here cos h minus minus makes 0, and ln of 0 is infinite. The minus cancels, so I have infinite. So that means the inverse of the correlation length is infinite. That means that the correlation length is 0, which means that the correlations break down at high temperatures. Okay, so this is the boring results of the 1D Ising model. But as I said, it's actually very useful to look at these results because they teach us about the lower critical dimension. And so to yes.
It's confusing. Wait, so it says rho to the power or whatever that is, the power of -1 goes to 0 for h equals 0, but that means the correlation length goes to infinity, but would we expect the exact opposite behavior, that for h not 0?
So we take, now it's the question, maybe I screwed up taking the order correctly. So you're referring to this, right? Yeah.
Yeah, right.
Okay, let's look at it. So the correlation length should be right. So so we're taking, if you take beta, if you have h0, having taken infinite, so 0 correlation length, I can follow your argument, and I agree that I would also wait. So okay, so here we have this case, and this is correct. So this means that correlation length is 0. There's no correlation left at high temperatures, and we expect here actually the other case around. So now the question is if, no, but that's, I think, okay. So most likely what went wrong is that so we would expect for a finite, okay, so we take the temperature to 0, and we want to have a field, and if we have an applied field, I can follow your argument. I need to look it up. Like it made total sense to me yesterday. It doesn't so much right now, but this is like standing in front of a blackboard, and that sometimes doesn't really help. I will look it up again. But let me go to this to the frustration of why the 1D Ising model is kind of boring, because we only have this a tad of a phase transition at this state that we won't ever reach anyway, right? Which is at 0 temperature, right? I mean, how boring is that? So let me ask the question, why does the 1D Ising model not exhibit long-ranged order at a finite temperature? And this goes into the so-called parallels argument. Which we're going to lay out. And I think it's best explained in Shojuri, chapter 8. Okay. Suppose there was long-ranged order. So we examine the system at a temperature that's below the critical temperature, where we expect most spins to be aligned. Right, so we do lots of these spins, and most of them are aligned in the same direction. Okay, so say this is n spins, and so the energy of this system I can write down as minus n minus 1, which are like the number of interactions I have in between these n spins times the interaction energy. Now what I can do is I can go in and say I pick these spins and I flip them. So here I pick a block of spins and flip them. What does it cost me in energy? How much do I have to pay for this spin flip? Do you know? So I have like all these, each interface costs me.
So for next neighbor interaction, that's 2 times the interaction energy.
2J, right? So this is a simple cost, like it's a small cost, because this goes with the energy cost of flip is 2J.
It's actually 4J, right?
No, so each so I sum only nearest neighbor, so this costs me 1J, and this is another J.
Yeah, but I mean, you have plus J to or minus J to plus J, so it's twice the J for one spin flip. This is my logic. Unless there was like a 2 defined somewhere, but like I mean, okay, it's a prefactor. But
so I flip from
in the exponent there's minus J Sj times Sj plus 1. So if I was parallel, there was minus J. If I was anti-parallel, there's plus J. So the difference is 2J per flip spin. And I have 2 flip spins, so
yeah,
it must be 4J.
that's okay. Yeah,
But
it doesn't matter.
again,
It doesn't matter. Let's make it 4J. It's a finite small number. But let's make it 4J. So this is 2J and this is 2J. And yes. But in principle, I can have the spin flip at any of the locations, right? So it doesn't need to be as here starting between flip spin 3 and spin 4, but I could also have the spin flip, say, at this location, right? And it would be the same cost. So I have a lot of choices of where, if I were to have this energy of 4J, of where I could have these spin flips, and also how many spins I could flip, right? Because I only pay for the boundary once, so I could flip 5 spins or 10 spin. It's the same cost. But the big argument is that, you know, I have lots of choices on where to do it. So but beginning and end of block and each be in n2 minus 1 places. So there's an entropy gain with flipping. So the entropy gain is of the flip is 2 kb ln n minus 1. And so now for sufficiently large n, we always have that the entropy gain is 2 kb ln n minus 1 is always bigger than 4j. Look here, my notes are consistent. So like obviously for a small system, the entropy gain is not really big. But the bigger my system is, the more locations I have to put down this the spin flip. And so the entropy gain of having such a spin flip goes up. And so since the free energy, which actually governs the dynamics, is accounting for both the energy and the entropy, the net free energy is actually destroying any long-range order, because it's such a small energetic cost for this little interface that I always gain in entropy. And so this is why we would not expect any long-range order for the 1D Ising model. So entropy wins. So, but what's the way out, right? So, okay, so the 1D Ising model, I think we've given up hope, right? You know, because it's entropy will always win over energy eventually. The energetic cost of a spin flip. But what can help us here? What can help us is going to higher dimensions, right? So note this entropy and energy balance is dimension dependent. On the spatial dimension, the lattice. So in d = 1, the energy cost is independent of a okay. This is much better than on any of the other corridors. You know, the old ones that are not renovated, you still have these brick floors. It's amazing. Like, did I mention that my office is luckily in a different building? It's like crazy. Like, you know, if they're moving any lab supplies, it's like you have a train just passing by because of like this brick layout. I don't know, we had this. I mean, I kind of like the cozy feel that you get from the red brick walls, but on the floor, they didn't think it through, really. Oh gosh. So in D1, energy cost of a block spin and my block, I'm sorry, like I don't know why my I thought my blocks flip is independent of block size, but this rapidly changes if you go up to higher dimensions. So for example, in D equal 1 or bigger, if we like, I think it's easiest to imagine it for 1D, for 2D already, right? So if I here flip spins, right, in this ocean of say as I've flipped these 3 spins now, I pay more, and how much I pay also goes up with the number of spins that I flip, right? And so the costs of flipping various spins is much higher, and actually grows with a power law, and therefore it can be the entropy gain of flipping spins is not that high, and like energy is actually minimized by aligning the spins, also at a finite temperature. So the surface energy increases with block size and the power law. And so here, ordering can be as it reduces the create energy. Okay, and so that's now the concept of the lower critical dimension. So this states the minimum dimension in which fluctuations are sufficiently costly to not always destroy long-range order, in which and so for the Ising model, the lower critical dimension is 2. And so that shows you that in the end, indeed, looking at the 1D Ising model is insightful, because we learn something about the nature of phase transitions and how they may arise. And this is the case for the 1D Ising model. I will show you next week of what the transfer matrix approach can be generalized to different models as well. Most of the formulas that we've derived today were already stated in a generalized form, but you can basically just write it down. I'll do this early next week then. Any more questions? If not, then thanks for being an engaged audience, and let me quickly stop the recording. Here.